Okay, good morning, all of you. My screen is visible. Hello. Good morning. My screen is visible. Okay. Okay, I'll see that last class we discussed the power diodes. Now there is a small comparison between the general diode and power diodes. So as I said, even construction wise also, there is a small comparison. N-1 drift region will be there. That is the major difference. Now apart from that, some of the comparisons we'll discuss in this slide, and then we'll move on to BJT. So general purpose diode and power diode, input bias voltage is greater than threshold voltage, that is a zero point 0.7, then the diode becomes on. So we require zero point 0.7 volts to turn on the diode, means anode to cathode voltage minimum voltage is required. Whereas in this power diode, forward bias voltage is greater than the threshold voltage, that is 1 volts is required because it is high rating of the devices. Then only the diode becomes turned on, and then it increases linearly. A low current and low voltage handling capability. Normal general purpose diodes having low current as well as the voltage handling capability. But whereas in the power diode, high current and high voltage capability. Generally will use as a, in general diode will be used in the low power circuits, whereas here will be used in the high power circuit. Like our power electronics controllers we are using as a diodes also, like freewheeling diodes or feedback diodes, whatever we are using in the case of inverters or in the case of rectifiers, we are using as a diodes as well. In that little bit as a high power circuits, all power electronics controllers are high rating capabilities. That's why power diodes will be used rather than the general purpose diode. Here we have used only two layers, that is a PN. But whereas here you can see that three layers, that is N-1 drift region is introduced. That's why we get it as a three layers here. And the lightly doped N-1 layer is not in the PN junction diode. So that means this N-1 is not present in this, whereas here N-1 layer is going to be present in that power diodes. And here impurity concentrations of the diode may not very large to layers, but whereas here impurity concentration of the power diodes are vary layer to layer. So whereas here may not be very layer to layer, but here it is varies layer to layer. So these diodes operate at higher frequencies, about hundreds of kilohertz, and this will be used under you can see few volts, and the frequency is below 1 kilohertz. This will be about some hundreds of kilohertz. You can operate general purpose diode, but power diode will be used frequencies below 1 kilohertz only. Available from few volts, that means 5 volts to 1 kV of power ratings up to 50 watts is available. But whereas here you can see that rating itself, it is a very important point here. 5 volts to 1 kV only available in general purpose, but whereas here you can see that up to 10 kV and amperes also 5 kilo amperes. This is the current rating, this one is the voltage rating available, but whereas here in the power rating only 50 watts. Here on state voltage drop is about 0.7 volts, and here will be drop about 1 volts. The reverse recovery time is low, that is 1 nanoseconds to 1 microseconds, and the reverse recovery time is about 25 microseconds. And now we'll move on to power BJTs. So all whatever devices we are going to discuss here, even if I'm not specify also, that treated as a power BJT, power MOSFET, power IGBT, like that. So power diode. So the reason is in this is all high rating applications only we are using, and the operation. Even though you may be known that the basic things of BJT, but here we are operating only in the two regions, not the active region. It will be either cutoff region or a saturation region. That means whether it is non-state or in the off state. So only these two modes of operation only we make use of it. So because our intention is not to amplify the signal, because BJT we can use amplifier also, no. But in our case, we will use only either it has to be completely on or it has to be completely off, like a switch. So that is our purpose, is that is the thing. So that's why preferably when it is operating condition and all, the drops must be as minimum as possible. So that is also another intention, because here high rating of the application we are using. But if your conduction resistance are more, or suppose the drops are more, obviously there is a power dissipation is taking place. That's why MOSFET is, that is the one of the drawback. There is a conduction resistance RD will be more. That's why whenever we are operating that, we'll get it as a more power dissipation. That's why MOSFET will be operate only low rating application. We cannot use for high rating application. But switching times are very small. That's why we can use as a high frequency operations, but not high rating operation when compared to the BJT and all. Now we can see that a bipolar transistor is a three layer, two junctions. Whether it is a NPN or a PNP semiconductor device. That junctions are, you can see that emitter base junction, and another one is a collector base junction. These are the two junctions will be available. Now you can see the structure. Normal, see that NPN transistor we can use. There is emitter, collector and base. Another one, there is a PNP also there. Preferably we use all NPN transistors, and emitter and base, then collector. So only thing is whether it is NPN transistor or a PNP transistor. Based on that, the structure will differ. BJT consists of three terminals. That is, terminals are, as I mentioned, emitter, collector and base. So on two types we have, that is NPN, another one is a PNP. When a single p-type semiconductor layer is sandwiched between the two n-type semiconductor layer, you can see that this one, whenever if you do p-type semiconductor is sandwiched between the two n-type. So if you sandwich this, that will make it as a n-type semiconductor layer, and that will formed as a NPN transistor. And similar fashion, you can see that single n-type semiconductor layer is sandwiched between two p layers, that is a p-type semiconductor layers. Then that will become as a PNP transistor. So that will form as a, either it is in the PNP or NPN. Based on this, between two n-type layers, if we sandwich that p, then it will form as a NPN, and otherwise it will be as a PNP transistor. Now current signal is applied to base. So this is a normal logic. In this case, it is a, in the previous class also mentioned, it is a current control device. So in this case, one advantage also there. What is that advantage? We don't require any commutation circuit. But if you recall in the previous one, what is that SCR? What we need is there, we required as a gate signal as usual. We are passing as a gate signal and it will turn on. But later on, we don't have any control over the gate. It simply device will starts conducting and it's go on conducting until unless if you reduce the current pass through, that will be the below holding current. In that case, what we need is to turn off the device, because all the devices what we required is only on and off, no. So that is the reason in every instant that depends. Maybe you may turn on some more time or less time, that may be vary, but final goal is any switching device. in our power electronics, we just turn on the device sometimes and turn off the device sometimes, then again turn on and again turn off, like that. So that is our process. But in SCR case, once device is turned on, we need to use some circuit or some mechanism to turn off the device. That is a forced commutation circuit. But whereas in the case of BJT, that is the one advantage you can say. You can turn on the device using gate current, or I mean base. If you pass the base current, automatically or signal, it will be turned on, and you remove it, automatically it will go off. So we don't require any commutation circuit in this case. That is the another advantage, you can say that, because all these points will summarize and will make it as a comparison between. That's all. What I did in the earlier power diode and then general purpose diode. Now we'll discuss the BJT, then we'll compare the BJT and SCR. Then we'll discuss MOSFET and we'll compare BJT and MOSFET. Then we'll go for IGBT and all compare it like that. So that is the comparison of the last topic of this unit. The current signal is applied to base, then what will happen? Device will be on. When the control signal is removed, so that means base signal is removed, then what will happen? Device will be turned off. Similarly, whereas if you compare to MOSFET side, what will happen? The voltage signal is applied to gate. Anyhow, another topic is MOSFET only. There we'll get in detail of that. Just in continuation of this, I mentioned that because of this is a current control device, but MOSFET is a voltage control device. When voltage signal is applied to gate, then what will happen? Device will be on. And if you remove the signal from the gate, then automatically it is going to be turned off. By imaging the analogy of a diode, transistor can be constructed like a two diodes. So that connected together. See, it is very simple logic. You know the diode. Just we are using as a one diode here. What is that? PN junction. This is a P and then N. And if I add one more diode like this, now you can see what is this? This is N, this is P, no? Then it is a PNP transistor. And similarly, what I want is NPN transistor, let us assume that. Now, this is a P, N. Now again, I will make use of another diode. No, that's it. So this is a NPN. So by analogy means just make use of two diodes. Based on the connection, it may be formed as a PNP or a NPN, depends on our requirement. So that's what I mentioned here. Two diodes you can use to form as a transistor. It can be concluded that working of transistor is based on the work of the diode. So because we are using the two diodes in anti direction side, whether it is an PN or a PNP transistor. Now that's what you can see here. There is a BJT, how it will be formed as NPN or a PNP. This is the one of the diode and this is another diode. So between these two, it is a P and upper side is N and this is a N, then it will form as a NPN transistor. So the symbol of NPN transistor will be like this. There is a collector, then emitter, then base. This is a NPN transistor. Similarly, you can see that this is a symbol of transistor, just I mentioned here, no, same thing. What you can use as a emitter, and this one is a collector and base. If we pass the signal to the base, then the device is going to be on. If device is on, automatically current flows from collector to emitter. That's all. So how the device is going to be on? By make use of a base signal. That's all. So that is one of the transistor type. Now from this diagram itself, we can see that emitter current. How we can write the emitter current? Sum of these two currents. One is the base current, another one is a collector current. So that will become as a emitter current. So that is the one relation. And similarly, you can see that PNP transistor, and again we make use of the diodes only, will form as a PNP transistor. So this is the direction of current will change obviously. Now we can see that emitter current in this direction, base current, and then collector current. Now this is a symbol for this. This way also you can represent, or you just reverse it. Emitter will come downward side, and we can make use of same model also we can make it, but current direction will make like this. So that is the difference. This way also same. Now what will happen? Collector current is equal to the emitter current minus base current. So this is the case of PNP transistor. So this is just internal structure how it will form by make use of a two diodes. It is NPN transistor as a PNP transistor. So whatever arrow we indicated, that direction of the emitter current. So that is will represent, same thing will represent in MOSFET also. And NPN and PNP transistor have two PN junctions. One junction is formed between emitter and base, and then this is called as a emitter base junction, or simply we call it as emitter junction. The other junction is formed between base and the collector, so that we call it as a collector junction. The another name, instead of representing collector, because base is common for both, so that's why there we call it as emitter junction, this we call it as a collector junction. Now you see the some applications of BJT. There is, we can use the televisions, transistors, we can use mobile phones, we can use computers, then radio transmitters, and then audio amplifiers. So use of modulators. So these are the some of the applications of a BJT. And now the characteristics of power BJT, you can see that large size and the higher breakdown voltage, and then higher current carrying and power handling capability. When comparatively MOSFET, this will be as high carrying capability. That's why I told no, there is a MOSFET will be used for low rating application, but high switching frequency operations, high on-state voltage drop, and power application. So high power application will use as a power BJT. And now there is a classification of power transistors. You can see that BJT, because all transistors we can divide here, no, BJT, MOSFET, and IGBT. So these are the three things. So in our syllabus we have only this diode, then BJT, MOSFET, IGBT. So after this we'll go for MOSFET and IGBT. So bipolar transistor can operate within three different regions. So this transistor, three different regions are there. One is active region, but in our case, wherever we use this device, we won't use the operation in the active region. What we'll use is either cutoff region or saturation. We'll use only that thing because it is a switching action. And this operates an amplifier. Only active region means it will be operated as amplifier case, but our case is not amplifier, we don't use this. And saturation, that means fully on. Saturation means collector current, it carry the current, load current, or wherever you connect that will carry the current. That's why IC is equal to I, that is a saturation. And cutoff means it is fully off. We will use this device only at this operation. So either it is completely on or completely off. So that means the IC is 0, that is going to be as a cutoff region. Common emitter current gain beta and common base current gain is alpha, that will be represented here. If you use as alpha is IC by IE, or IC is equal to alpha into IE. Similarly beta expression, there is a small relations between this transistor case, collector and emitter, and common emitter current gain, as well as the base current gain with some relations we have mentioned. So as I said in the previous slide, there is a emitter is equal to, means emitter current is equal to collector current plus base current. So that is the relation, because I mentioned in the diagram also. This is the emitter and this is the base, and this one is a collector. So that's why emitter current is equal to collector current plus base current. And now emitter, all these terminals are given one single sentence. Emitter supplies the charge carriers, and they is heavily doped so that it can be inject the many charge carriers into the base. and the size of the emitter is always greater than that of the base. And another one is a base terminal. This is a middle layer, so called as a base. So you can see either it is NPN or a PNP transistor. The middle layer we call it as a base. Base of the transistor is very thin as compared to the emitter and collector, and it is a very lightly doped. Another one is a collector. The function of collector is to collect charge carriers. So another one is the moderately doped. When compared to other base and then emitter, it will be as a moderately doped. And this is doping level of the collector section is between the emitter and base. And size of the collector is always greater than the emitter and base. And the collector area is the transistor is considered larger than the emitter area. So in the area wise also, but these all just basic information, whether you want to write in exam or not, only to know the terminal characteristics I'm representing. There we can represent directly structure as well as the input and output characteristics, because of the collector region must handle more power than the emitter, and the more surface area is required for heat dissipation. So if the surface area, this is also one problem, the heat dissipation has to be uniform. Otherwise, a hot spot will be created and the temperature will be rise at the particular instant. The device is going to be damaged. That's why more surface area is required for a heat dissipation purpose. Now there is a water analogy of a transistor. You can see this. Emitter, collector, and base. As I mentioned, in a transistor, there is a three terminals. So what are the three terminals? One is emitter, another one is a base, and then collector. So now here, the base is a control area. So if base is like a tap, a control parameter. So now if you open this little bit, then will flow from emitter to collector. So let it be just water analogy. The water will flow like this. If we completely open, more water will flow. So like that, it is just like a tap or water. So here water is a current, nothing else, and voltage is a force on that. So that way we can say that is a analogy. You can see now. Just I open little bit, then what will happen? It will flows from emitter to collector, and if I open further, fully open, then more electrons will flow to that. So this is just analogy I'm showing. Then once if I close that, close means it is off state, then it won't happen anything. So it will be completely stopped there. So this is the analogy of the transistor and structure of the power BJT. Now we can see that again all the structures, whether it is a BJT or a MOSFET or anything or IGBT in a power device, we required this drift region. We are adding that. So other than that, everything is similar. There is what is the width of that layers, all these things is specified. Base thicknesses and collector drift region. This is the drift region. So all parameters are mentioned. Whether you want to use it, this if you remember, you can use it. Otherwise, just represent the structure and then you can explain the characteristics. That is sufficient. So now we'll see that a power BJT has a 4-layer structure because N minus is added, and alternating P and N type doping as a just shown as a NPN transistor, and it is most power electronics application. It is operating as a common emitter configuration. So normally we'll use the common emitter configuration. The base is the input terminal, and collector is output terminal, and the emitter between the input and output. So this is the connection orientation. And power switches, NPN transistor most widely used than the PNP transistors. Normally in our case we will use only the NPN transistor in our as a switch power electronic. Not only choppers, you can see that choppers we can use as a thyristor for high rating application, but normally there will use as a transistors, MOSFET and all. Even inverter also, low rating of very high rating application only will go for as a SCR and all. Generally SCR will won't use for the inverter case. There will use IGBT or a transistor or a MOSFET. All low rating case will use BJT. Otherwise, we can use as a MOSFET for inverter application. In our house inverters and all, normal small size inverter below 1 kilo kVA rating and all, will use as a MOSFET. Even they don't use IGBT also. It is very small rating, because our output will be make it as a sinusoidal in nature. For that higher switching frequency operations we need to do, that will come under pulse width modulation techniques. For that reason, high switching frequency device is only the MOSFET. So that is the reason. But power dissipation, when it is a low rating case, that's why we can able to neglect that. But once if you are using as a high rating application, MOSFET cannot be used for that application, because very little bit conduction resistance is more. So that is only the problem. Now you can see that base thickness as small as possible to provide good amplification capability. That is the normal case of BJT. But here, our requirement is on and off. Due to very small base thickness, breakdown voltage capability is reduced. So breakdown voltage capability is reduced because of the base thickness is small, and lesser voltage is sufficient to break that. So therefore, what will happen? Thickness of power BJT must be more compared to normal BJT to increase the breakdown voltage capability. So thickness of a power BJT must be more compared to the normal BJT to increase the breakdown capability, voltage capability. That's the reason we are increasing that. Current gain of a BJT is small, about 5 to 10. To increase the current gain, Darlington pair BJT used. So two transistors we can combine that way, we can get it. And steady state VA characteristics, and then we'll go for as a dynamic characteristics. So this one is the normal transistor, and how the input characteristics for common emitter configuration. You can see that input is a base. As I mentioned in the previous, input is a base, and then collector is the output, and this one will be as a common. So now we can see that when input current, because we required as input characteristics, so VBE. So VBE is nothing but a base and emitter, and this is the input side, and output side is this one. So now what will happen? You can see that we fix the collector to emitter voltage. Some voltage you can fix it, and then you can just vary the VBE. If you vary this VBE, if threshold voltage reaches, automatically the transistor is going to be turn on. So our intention to turn on the transistor. When it will be turn on, once the threshold voltage reaches, so then automatically this linearly varies that. So if you are increasing VCE, that is a collector to emitter voltage, then automatically the characteristics will be vary, and so on. We can vary that voltage, and you can get it as a different characteristics. So that's what I mentioned here. Base current and the emitter voltage is input side, and then base emitter junction of a transistor like a diode, and the VB versus VBE is plotted here. And when the collector emitter voltage, that is a VCE2, is more than EC1, the base current decreases. So because we don't require much base current, because we already increased the voltage, that's why base current is going to be decreases. Now the output characteristics, you can see there is a two plots here. So one plot is related to power BJT. This one is a normal BJT. So one major difference we can notice here, quasi-saturation region will not be present in case of a ordinary BJT. So now we can see this this region. This is the additional region will be present in case of a power BJT. So that won't be there in case of a ordinary BJT. So this is one thing, and then secondary breakdown also is there. And this is the slightly different with comparatively ordinary BJT. So there we have cutoff region, and then active region and saturation region. These are the three regions, but we will get it as a four regions in this case. So that is the quasi-saturation also will come into the picture. We'll see that there is a collector current, and then collector emitter voltage, that is a VCE, is given as a output characteristics of a transistor. Because I mentioned, no, base is a input, and IC base current is input, then collector current is output that we are representing. Now initially suppose if base current is 0, then VCE is increased. So if I increase the VCA, it won't be turned on, because the base signal, if you are not passed, then automatically device will not be turned on. So that will be as a 0 only. So that means very small leakage current only we pass through that, but the device will not turn on. Now if I increase the IB instead of 0, on that time this is same. Now the process is same, only additional structure will be formed, that is n-1 drift region, and because of that we'll get it as a quasi saturation also in that. And now we can see if IB is 0, that we call it as a cutoff, it won't be turn on because it is a off state. Now I increase IB some value, IB1, IB2 and so on. If I increasing gradually, see that IB is 0, then IB1, then IB2, IB3 and so on, gradually increases, then collector current also rises, because if I are increasing the base current, automatically collector current also going to be rises. Therefore, 4 operation regions are present in this power BJT. One is a cutoff region, another one is active region, and quasi saturation and hard saturation. But that will not be present in the case of quasi saturation is not present in the normal BJT. And since it is used for switching purpose, now it is not amplifier, I already mentioned. Only amplifier case there is active region, but under switching purpose we don't want to use as a amplifier. It will not be, either it is operated in the saturation or a cutoff region. Saturation means it will completely on, and cutoff region means completely off state. And quasi saturation occurs due to lightly doped n-1 drift region. So this is the present in that one of the layer we added, so that's why that will be formed. So cutoff region, when IB is almost 0, so then no collector current, then output is 0, that we call it as off state. If no current, automatically device will be in the off state. So quasi saturation and hard saturation, the base drive is applied. Whenever the base current is applied, then only it will happen, the transistor set to be on, and hence what will happen, collector current will flows. And primary breakdown, here 2 breakdowns will be there, primary breakdown as well as secondary breakdown. The primary breakdown will be takes place because of the avalanche breakdown of a collector base junction. So if that collector base junction is breaks down, then automatically already other junction is forward bias, and if that junction is breaks down, then it will allow current pass through that. Therefore it is a on process. Large power dissipation normally leads to the primary breakdown. So the power dissipation is takes place, that is nothing but a primary breakdown. And the secondary breakdown, when power transistor operate in active region with a large IC current, there is a voltage drop across the collector emitter junction. So if suddenly collector current increases significantly, there is a large power dissipation within the device. This is the major problem actually. If that is happened, then automatically there is a large power dissipation is takes place within the device, but the surface area must be increases. Then only that dissipation is uniformly distributed. Otherwise, automatically hotspot will be created. So this situation is very dangerous. Power dissipation is non-uniform, spread over the entire of the surface area. Then the consequently local hotspot will be developed within a device. Then local hotspot means in the particular area, it is unable to spread that dissipation, or you can say the temperature, then the breakdown is going to be occur. So that the device completely damaged. If that thing is happened, it is not in our hand to control. It is unwanted triggering, like we noticed in the case of temperature triggering. No, that is unwanted. That's what we minimize to temperature rise. We are using as a heat sink. So that is the problem. Then the breakdown is called as a secondary breakdown. So this can be avoided by snubber circuit. So the snubber circuit, it should not be rise the voltage suddenly. To minimize that, we can use as dV by dt triggering, like what we mentioned in that. Now we'll see the dynamic characteristics of a BJT. So whatever we mentioned in the previous one, that is a static characteristics. Now dynamic characteristics, like SCR here also, we required to turn on the device. We need some time, and if it is already on, need to turn off the device, that we required some time. That process we will explain, nothing. See, simple thing, collector current. What is meaning of collector current? If the device is on, then only collector current will be present. If device is off, what will happen? Collector current will be zero. In that logic, I mention as a collector current, you can see that initially device is off state, collector current will be zero. Now we are trying to on the, from this point onwards, we are trying to turn on the BJT. How will you on the BJT? As per our logic, we need to pass the base current. So before that, base current also zero. Why base current is zero? We didn't turn on the device. So device is off state. That's why we didn't apply any base current. So base current will be zero. Then collector current also will be zero. But there is a voltage across collector and emitter is there. So now later on, I want to turn on the device. That's why I applied the base current. If base current is applied, then what will happen? Device is going to be turned on. So it is from zero onwards, it's gradually turn on the, it's going to be turn on the device. So once if device is completely on, then what will happen? This collector current will be present, because how long it will be on? Until that will remains maintain the collector current. Once it maintain the collector current, whenever you want to turn off, then what will happen? We are it is the collector current is gradually decreases and finally reaches to the zero. If the collector current is zero, that means automatically device is going to be turned off. So once the device is on state, because the this is the device, what we call it as collector and emitter voltage. Collector and emitter voltage, if it is open, will be there, but once if it is on through base, if you pass the base current, the device is on, then what is voltage across this? It is dropped down to very very low level, no, like a zero. So that's why during on condition will represent as a zero. But what about the collector current? It is passing the current, that's why we'll make it as a current here. And once it is off, during off process, that current will be gradually decreases and finally reaches to the zero. That will be off process. And on process, initially zero, and it will become turn on. Once it is on, it will maintain as a collector current. So this is the very simple logic what will happen during off state and on state. So that is a dynamic characteristic. We'll see that what is happening here, delay time, then rise time. So this portion is a delay time from 0 to 10 percentage of the final collector current, and then this is a what we call it as a rise time. So some of these two current I call it as a turn on time. So that is a T on process. So delay time plus rise time. And now we can see that off also we have two intervals. So during this instant, TS plus TF fall time. So that will consider as an off interval. So like that we can easily explain by drawing this plot step by step. First we'll see the turn on process. Turn on process consisting of two things, one delay time, another one is a rise time. Now delay time required from collector current to 10 percentage of its steady state current. So in the same time, we can see that VCE falls from 100% to 90%. So it is rated initially, then it is falling to little bit as a 90 percentage of the VCC applied. That we call it as a delay time. And rise time. What will happen rise time? It is straight away, you can see here, collector current changes from 10 percentage to 90 percentage of its final value. That's it. Directly we can mention it. At the same time, what will happen? This voltage, no, from 90 percentage to 10 percentage of its final value. That interval we call it as a rise time of that. Then sum of these two. What we can do? Sum of the delay time and then rise time, TD plus TR, will give as a turn on time. And this turn off time typically 30 to 300 nanoseconds. So this is the turn on time will be 30 to 300 nanoseconds, but this is the time taken to turn on preferably. There is, I mentioned in thyristor also, no, 1 to 4 microseconds of time like that. So now turn off process. So what is the turn off process? TS plus TF. This is a storage time, and then there is a fall time. So sum of these two time we call it as a turn off time. So input voltage again changes from positive to the negative, then it become base current will be negative gradually. Once the base current is negative, then automatically excess charge carriers will be removed from the base, because already on state we stored some excess charge particles like a thyristor also. We remove that excess charge particles we are using there in the reverse recovery time and gate recovery time, whether it is a outer junctions and then inner junctions. So inner junction recombination process and all, whatever means, if you do that, the charge particles are completely removed, then only the device is going to be turn off completely. And now the collector current cannot be changed immediately, but the value gradually decreases. That's why you can see that the gradually, once if you are removing the charge particles, the collector current will be gradually reduces to the zero. The time interval between the instant of the changeover from input voltage positive to the negative, the instant collector current, you can see here, there is a collector current from 90 percentage here and reaches to the 0 point. So that's what we mentioned here. Collector current falls from 90 percentage of the steady state current is called as a storage time. So that from 100 percentage to 90 percentage of time, we can call it as a storage time. And later on, from that point to the 0 point, we call it as a fall time. So during storage time, the collector emitter voltage increases from VCE to 10 percentage of its VCC. So, and all excess charge carriers will be removed during that instant. The applied negative voltage can be increased. The rate of removal of excess charge from base, subsequently the storage time of turn off time will be reduced. So obviously, once if you are increasing the applied voltage, so removing the charge particles will be faster rate. So now the turn off time, one is a storage time explained, then there is a fall time. So fall time, we can see here the current fall from 90 percentage to the 10 percentage of that, we call it as a fall time. So now this one is a 90% and it will reaches this point, we call it as a fall time. So that's why I mentioned here 90 percentage of steady state current to 10 percentage of steady state current. The collector emitter voltage increases from 10 to 90% voltage. So collector to emitter voltage increases. What is meaning of VCE increasing? Because there is a device, the device is on means that voltage will be zero nearly, because it is short, no? Device is on. But once the device is going to off, then what will happen? This voltage will be developed, and once completely off, then that voltage is same as the source voltage. So whatever voltage will make it, that is a collector to emitter voltage, will get it as a higher voltage. So that's what, whatever we applied VCC, that will become. So once if it reached, that shows that the device is completely off. So that is a turn off time is the sum of the storage time and fall time, that we can represent as a turn off time. Now this is also 30 to 300 nanoseconds of time. So the merits of BJT, we can see here some of the merits also there, as well as the demerits also there. You can see BJT does not require commutation circuit. That's initially I mentioned that. Why? Because the BJT is controlled by the gate. Once if you remove the gate signal, automatically BJT will turn off. In that scenario, we don't require, the device is going to be turn off by make use of a commutation. The only thing is we removing the base, automatically the device is going to be turn off. And have small turn on and turn off times. As we mentioned that 30 to 300 nanoseconds of time, turn on time or a turn off time. The BJT shows better performance at higher frequencies, and base drive has full control over the operation, because base is only the control point in the case of BJT. both sides, off side or on side, and it has a small um, turn on losses. So turn on losses are very small. Of course, that is only our requirement actually. Turn switching losses will be minimized. And demerits you can see here, this will be low switching frequency. Means on and off intervals it will little bit taken when compared to other devices is fine, but still we need to improve the switching frequency. Like once if we compare to the MOSFET, this has a low switching frequency, and drive circuit of BJT is complex, and BJT produce more noise, and the negative temperature coefficients is create a problem in paralleling. So here, when you want to operate BJTs are in parallel, it is not possible because of the negative temperature coefficient. But whereas in MOSFET, positive temperature coefficient will be there, we can operate that into parallel. That will come later. Storage charge in a base reduce switching frequencies, because storage charges is a base will store some, that to dissipate that charge particles we need some time, that because of that time what we call it as switching frequency is going to be reduced. And now we'll see the comparison between the SCR and BJT. So in the earlier version, we compared between power BJT and power diode and general purpose diode. But now step by step, if we move on, already we discussed the SCRs. Now we'll compare with SCR. Later BJT and MOSFET, and then MOSFET and IGBT, like that. And in the exam they may ask that compare all the three also, BJT, MOSFET, IGBT. Then whatever comparisons are there, you just make it as a table, will represent all the three comparisons. Now you can see the SCR, that 4-layer PNP device, and then normal BJT is a 3 layers only, PNP and then NPN transistor. If you strictly speaking power BJT, there is N-1 layer also present. And then turn on by regeneration, no regeneration exists. Here we will pass only the base current, it will be on, and remove it, it will be off. Gate has no control over the SCR once it is on. That is the problem I told in initial in the SCR case. Once SCR is turned on, then whether gate signal you give it or you remove it, it won't happen anything directly, it will continue to conduct. So that is the reason gate has no control once the SCR is turned on. But whereas in the case of BJT, gate is fully controlled. What will happen, whether it has to be on or off, so automatically base signal is going to be removed, or you can give the base signal. And external circuits are required to turn off the SCR. That means forced commutation circuits are required. But whereas in the BJT case, we don't require, no external circuit is required. It will be turned off by drive is removed. Means base drive is removed, then automatically device is going to be turned off. And then false triggering takes place if dB by dt is exceeded. So that is the problem in SCR also. To limit that only, we make use of snubber circuit. But there is in the inverter case and all, false triggering is very dangerous. That's why false triggering takes place if dB by dt exceeds. So there is a specified dB by dt rating is there. If that rating is beyond the specified, automatically the thyristor will trigger. And whereas here BJT is damaged if dB by dt is exceeded. So used for control rectifier, where we can use SCR. So SCR can use all the controllers like AC regulators or DC drives, or in the choppers or inverters, like that. But this will be used in the inverters, low rating inverter, UPS and AC drives, and then SMPS, switch remote power supplies. So for this application, we can use as a transistor. So in the next class, we'll see the MOSFET. I think next hour EM3 will take, I think EM2 or something. EM2 will take. And I need to conduct one slip test for the second unit. When you can write any CR? Hello? When you will write, you just tell me the date, then accordingly I will conduct. What about unit 1 means? That's why I'm asking when you are ready to write unit 2. Unit 2 slip test is for slip test 1. Okay, then I will decide and I will let you know. Okay. I think Wednesday I don't have class. Wednesday. Yeah, otherwise Tuesday I will conduct. No problem, no? Yeah, choose. Yeah, no problem. No problem. Yeah, that's why at any your convenient time because it is online, no issue for me. Automatically that will open and you can write the exam. I will fix the time also there. Just go there and you can write it. Okay, next Thursday is your first sleep test. The syllabus is Unit 2, SCRs. Okay, and I think I need to take some more classes. Today I have some another work. Uh, so today afternoon, is it possible after college hours? Can I take that way? Anybody? Extra hour I'm asking. Hello? Okay, no? Today Friday. So preferably I will take because I have some inspection there. After that, I will let you know time and if tomorrow also based on I will inform you the time, but you be ready because I will finish it. This two more classes is required, MOSFET and then IGBT and all. Then I will start that rectifiers. Okay. Yeah, next Thursday. Okay.